Well, it's time. Welcome back, everyone. So we're on the last instructional week of the semester. Congratulations on getting to week 15. Feels like we've been through a lot over the course of the past 14 weeks. But this week is solely dedicated to reviewing for the final exam. And for just a quick rundown of the announcements, this is our last quiz, number 12. We have several extra credit opportunities, and I might as well just start there next. The first extra credit opportunity we mentioned before, if you had an exam that was maybe not your best, if the final exam is greater than your minimum grade amongst these three exams, your final exam grade will replace it. The other extra credit opportunity is relative to the course evaluation. That's the pop-up that you might have been seeing when you're entering into any Canvas course for doing a course evaluation. If you've completed your course evaluation for this class, all you have to do to get this extra credit is send me a quick email message or a quick message through Canvas messaging system, and I'll drop your lowest 2 homework assignment grades in WebAssign. That way, if there's a rough WebAssign section or maybe just one problem that you couldn't get a section to 100% on, this can help out so that you don't get penalized too much on any odd section in WebAssign. Then last opportunity is to essentially get caught up for full credit. Any WebAssign section that's gone past due, we've mentioned all semester, you can make that up for full credit, as well as any quizzes that you have pending that you're behind on. The cutoff date for that is going to be Thursday of finals week, May 7th. So that's basically 11:59 p.m. on Thursday. But any questions at the moment, folks, with the announcement so far? Okay, well, this week is dedicated to reviewing for the final exam. So we will be going through these problems here. But first, we should talk about the final exam. Don't know why I took that away. It's pretty much going to be kind of the same rigmarole that you all did for exams 1 through 3. If you're in the online section, then early Monday morning, I sent you the instructions for scheduling your exam at your preferred testing center. And if you need to have that resent, if you can't find that message, just let me know and I'll send that back out to you. For the in-person section, it'll be in the classroom. For the classroom, it's Tuesday, May 5th. So exactly a week away from today, from 5:30 p.m. to 7:30 p.m. So it'll be this specific classroom, CHE 215. For everyone in the class, don't forget to have a scientific calculator. And the last page of the real final exam will be this document that you see here. Aside from that, there'll be other supporting materials. I hope you had a chance to take a look at any of these documents over the weekend. It was kind of a short weekend. Version 1, version 2 are the same parallel types of version 1, version 2 sample exams that we've been doing throughout the semester. But now these are comprehensive from the first section to section 5.3 we ended on. These are pretty long, so the idea is you're not necessarily going to open up, say, version 2, solve every single problem. They're more for targeting specific sections. So if there's one section that you found that's kind of trickier, maybe the chain rule section, or maybe, say, optimization section, anything along those lines, you can go to either one of these documents, target that specific section for extra practice. And these give you a good amount of problems. A more condensed sample exam is this file. This is all of the quizzes in the semester in just one spot. So you've done these problems before, but they'd be great to refresh on. Another good sample exam is put all of the exams together. I mean, that one has a cutoff. Not all of the information was on exam 3, so it only went up to the exam 3 section, which I forget is 4.4. So it leaves off antiderivatives 4.6, and it leaves off areas, distances, fundamental theorem of calculus. So keep that in mind, but I put this here just to convey the exams 1 through 3, questions on those are real similar questions that could be on an actual final exam. And so what I've done here is I try to do the impossible of condense everything that we've done in the semester into a representative set of examples. Our final exam is not going to be that long. I think it's about 12 questions altogether. And this one just gives us a good overview of what kind of questions you should expect on the real final. So that's the short one. And this is for looking into more practice down below. Well, that's my entire spiel. Any questions so far, folks? Okay, as you study for the final exam, it's a good idea to have this pulled up, maybe printed out. Don't bring it to the testing center, it's already on the exam, but have it pulled up on a screen or printed out just as a reference. Use that as you're studying because that will inform you where the formulas are, what formulas are provided. And as you're studying, if you notice that you need a formula not on that list, that would be considered to be a formula that must be memorized for the final. So this informs you of what's provided and also inform you of what needs to be memorized. So I have the full list of limit laws. We have table of differentiation formulas. So that's going to include the product rule, quotient rule, and other great stuff. The chain rule I felt like was a good one to cite, as well as properties of logarithms. This one's for exponential growth, exponential decay, including the half-life formula. Then I have the first derivative test for absolute extremes and the second derivative test. And the fundamental theorem of calculus is posted, even though we're not emphasizing it more than any other section. This is the new material, so I felt like it was a good idea to put a big block of that stuff. Indefinite integrals, essentially this is antiderivatives, provide us formulas as well. So this is all the information that you'll get last page of the real exam. And so what we'll be doing next, both today and tomorrow's class, is just working through these problems. I want to emphasize also, if you have questions that you'd like to take a look at any point, don't hesitate to throw them out there. You can interject at any point. There could even be multiple questions in chat. We'll do them in order. And if I just run out of questions, I'll just return to solving these problems here. And if there's any problems that I don't get to solving on the last minutes of Thursday, after I get caught up on grading on Friday, I'm coming back to this document, finishing out the whole set of solutions, and re-uploading it. So again, this is just a nice rundown of pretty much a lot of the main things that we did in the class. Not every single thing, because that took 14 weeks, right? But here is my summary of our class, Math 1160. First thing we're going to do is run through a few limits as a refresher. They're kind of scrambled, so they're not in the order that we did the limits in the course. They're mixed up on this document. They're a little bit mixed up on the real exam. So we'll cite what properties we need on each and every one as we go through. But to start off, you notice a square root that probably kind of tingles a bit of jogs in memory a little bit about conjugates. This one can be solved by just multiplying by the conjugate immediately to work out the limit. First, another thought maybe before we start on this one is try direct substitution first to see if it's plausibly a continuity problem. Direct substitution doesn't work here because we can't place a 0 in the denominator. So we're doing this step, multiplying by the conjugate, to try to algebraically simplify this down in order to eliminate that h. Once h is canceled, we will in fact use direct substitution. So we start by multiplying root 5h plus 36. It becomes a conjugate where we take that sign and flip it from negative to positive. Then multiply by the same quantity across the denominator, 5h plus 36 plus 6. And now we're just multiplying through, expanding as we go. Distributive law says we multiply here to here. But properties of square roots tells us if we take a root times the same exact root, we get to the thing on the inside, the radicand. So a square root times a square root produces the inner portion. So now this is nothing but limit as h goes to 0 of, on that first arrow in orange, we just pick up a 5h plus 36. And you could do these conjugates really fast if you got this pattern down. But I want to show the full expansion just to emphasize if you did expand it, this is what it looks like. If you did multiply here to here, this term eventually cancels, but at this stage it becomes 6 root 5h plus 36. And let's make that bar a little bit longer. Continue to FOIL through, multiply here to here. This is minus 6h, or excuse me, 6 times the root, 5h plus 36. And last, multiply here to here. That's going to give us minus 36. Across the denominator, we also multiply, but we're not distributing through. Our goal is to cancel off that h right there by the red dot. So we leave it in factored form, h times the group, root 5h plus 36 plus 6. So there it is. A lot of these mathematical problems get big before they start to resolve. But when we look at this, there are like terms in the middle. When we multiply it by a conjugate, there's always a cancellation on the middle terms. So if you didn't write those two in, that'd be completely acceptable. 36 negative 36 cancels. And now we just have a 5h divided by all that stuff. But because there's one term here, these things are multiplied, that h also cancels with this h. The sole survivor of the numerator is 5 after we multiply by the conjugate. So let's write that in. We're now looking at limit h goes to 0 of 5 over root 5h plus 36 plus 6. Notice there is no solitary term h on the outside. In other words, if you take h going to 0, plug 0 there by direct substitution, it's now allowed. This is a continuous function and the variable h at 0. So here's where we drop the limit statement, write in it's root 5 over the root 5 times 0 plus 36 plus 6. So now it's over, 5 is over just the root of 36 when we simplify. The square root of 36 is just 6. So this is 5 divided by 12. And that's the resolution for this problem. This tells us as h gets closer and closer to the value 0 itself, the result of this expression here gets closer and closer to 5/12, as close to 5/12 as you like, by making h sufficiently close to 0. But hey, that's one down. This one is a good review. I think conjugate is something you should expect on a real limit problem on the final exam. Any questions whatsoever for this one's rundown? Naomi says, when would we use the formula for f at a plus h minus f of a all divided by h? Or was this problem started in that format? Yeah, this was one of those kinds of problems. But for a final exam question for asking you to do that, it'd be more along the context of something like this. Find the equation of a tangent line would be asking you to do that. But even in this problem, I would probably just use the ordinary properties of the derivative to work that one through. So it looks like pretty much for this final exam we're doing, I didn't have one specific problem asking you to use the limit of the difference quotient as you stated. So it looks like we're just going to focus on these kinds of limits on the real final. Other questions at the moment? Okay, well, let's go off next to that limit. We mentioned on part A, first thing you want to do is eyeball it for a moment and ask yourself, what would happen if you really took 1, plugged it in for x here and x here? It's not like in the last problem, you can't put 0 there, it's undefined. So the limit still exists, but we can't compute it that way. But this one has no problem. The domain of an exponential like that is all real numbers. So this one is continuous, which means use direct substitution. There is really nothing big with this problem. If x is 1, then the limit of e to the power x squared minus x, as complicated as that looks, is just e to the power of 1 squared minus 1. Parentheses to show where x was substituted for value of 1. So now this is nothing but e to the power 1 minus 1 is what this resolves to, which is e to the power of 0, resulting in 1 altogether. So this limit goes really, really fast. As x gets closer and closer to the 1, the base e exponential gets closer and closer to a value 1 as well. Kind of a strange limit. The input x and the output, the limit of the expression, are the same. So that's one to expect as well. Again, these are scrambled, so part of the skill is for us to determine which process we have to use in which problem. Direct substitution, the continuity section, resolve this in one shot. The next one is algebra, just like part A. The next one after that looks like factoring of two different kinds. But any questions at all, folks, before we launch into part C next? Okay, I think there's one like this one on the real exam one as well. These ones are tricky. We just have to brush up on our skills with algebra, dealing with rational functions. So if you see something like this, a good first step is to just rewrite it. Limit as x goes to 0. On the first fraction where the red dot is, make it a little bit larger. Copy the second one, x plus 4. And all we need to get this going is a common denominator. We get the least common denominator by grabbing the missing factor, x plus 4, plugging it into here, which means we need to multiply above and below to not change anything algebraically. Now that we have x over x plus 4, x times x plus 4 in both denominators, we can do the subtraction across the numerator. So this gets us started, complete the denominators, and it becomes limit as x goes to 0, now one fraction, x times x plus 4. We can drop the times 1 in the parentheses and say now that this is just an x plus 4. Subtract across, so minus 4. And now we're on our way with this one. This one becomes really fast resolved at this stage. We can cancel the positive 4, the negative 4. You can cancel your x here as well if you'd like, but let me write it in as one extra step. Take the limit, x goes to 0 of x divided by x times x plus 4. So here's our next cancellation. That x and that x just vanishes. A silly mistake that I've made plenty of times is forgetting a numerator still exists. So I usually write a 1 there, extra protection, insurance against that mistake. Now we're looking at the limit as x goes to 0 of 1 over x plus 4. And you could have done that at this stage right here, but I'm just writing it in again as for the sake of clarity in the notes. Now at this stage, it's continuous, like on part A, part B. We can throw in 0 by direct substitution. 1 over 0 plus 4. So the whole thing 1/4 altogether. So kind of a strange problem. You couldn't use direct substitution first, because then you have 1 over 0 minus 1 over 0, or undefined minus undefined. And undefined minus undefined is not 0 because they're undefined. You can't do any arithmetic operation on those whatsoever. In fact, it's getting closer and closer to 1/4, not 0 whatsoever. So again, the algebra I'm going to try to not let get kind of any ways out of control. I think the trickiest one to expect for limits might be the conjugate, because of just by its nature, the algebra seems to just get big when you write out the full thing. But expect something with continuity, expect a kind of a fast fraction problem without crazy algebra. And you should expect something that might involve factoring as well. That'd be a pretty common problem. We mentioned this one has two kinds of factoring, but we can start off numerator and denominator in the same way, pull out the greatest common factor from both sides. So let's treat this as two factoring problems, duct taped together. Limit as x goes to -5. You might be able to factor this immediately as it stands, but to me that's tricky. I'm not great at factoring by trial and error when the numbers get larger. So I would absolutely encourage factor a 2 out first, leaving behind x squared plus 3x minus 10. Likewise, in the denominator, x factors out, leaving behind x times x plus 5. And I'm not going to make the factoring extreme. You shouldn't have to use the fundamental theorem of algebra, or excuse me, yeah, the quadratic formula rather. You shouldn't have to use a quadratic formula to get a factoring to force through some way, somehow. I'm not going to use like difference of cubes or any kind of strange factoring formulas. It should be along these lines. Similar things that we've been doing in class, you've been doing in homework all along. Still factors, so we continue on this. Limit x tends towards -5. My go-to method, because I don't make the factoring problems too complicated, we'll want to focus on the calculus, meaning my go-to method is usually trial and error, but let me fill in the denominator. Trial and error means grab the x squared, factor that as x by x. Next thing we do in trial and error is minimize the amount of trial and error as much as possible. If you see a minus right here, it's an automatic guarantee the signs are opposite of each other. So go positive, negative. Next, factor your 10. Sensible thing to do with the 10 is like a 2 and a 5. And if I just drop them in, it might be correct, it might not be correct, it's trial and error. You might put it in a better way if you're thinking about it, looked before you left. But this is what the check always looks like. Multiply here to here, that's a -5x. Here to here is positive 2x, and if you add those together, you get -3x. Doesn't mean start over, it just means swap your factors. So let's move the 2 around, the 5 around. So if you go that route, check your work. This is now -2x on the outer product, 5x on the inner product, and adding those together balances at 3x. So that solidifies this is our correct factorization. There is a massive hint though. The massive hint about this is for this limit to work, -5 had to go away, right? Which means you're expecting an x plus 5 above and below, so you can cancel here and plug in -5 in that spot and not get a 0. So that's usually a pretty good giveaway for these kind of factoring problems, making them even faster. Now we're going to direct substitute in just those 2 remaining positions, finalize the limit. Any questions at the moment with any of the algebra to here? Okay, so this has pretty much been the rundown on all the limits. Same kind of stuff we've done before, just different numbers, slightly scrambled up because now it's the final exam. We are not going on a section by section basis. Last thing is that this limit is 2 times -5 minus 2, divide by -5. Where the cancellations occurred, we're ignoring, we're considering them gone. And that means the numerator is going to be 2 times -7 for -14ths over -5. So it simplifies to a 14/5 altogether. So that's our last limit. Even though these limits were scrambled, most of the problems on the real final exam is pretty much in order that we did the course. A couple times I swapped problems just to make them fit better on paper. Like if I had something printed out, some kind of graph, and I couldn't fit the full problem, sometimes I swapped problems just to make it fit better on that page. Aside from that, most of the problems are kind of in order. We started with limits, then we went to tangent lines, so that's our next example. Well, any questions at the moment? Okay, well, as far as this one goes, we want to find the equation to, just notice that this one is not fully well stated. Let's say tangent line to the function below. I think it's a better way to say it. So I just noticed saying y sounds awkward when you write it out that way. Find the equation line to the function below, that one, at the point -5, 1. Then let's end the sentence. Sorry for the rough draft of fixing the wording on this one. I worked a little bit harder on the wording for the real final exam. I guess I threw this together kind of fast over the break, over the weekend rather. After we get the tangent line, this is a new kind of problem that you should expect on the real exam. I don't think we've done this one in class, but I'm going to ask you to directly sketch it as well. But you know, your sketch doesn't have to be perfect. My scale isn't that great. It's going by fives. You could even, in fact, start this problem right now if you wanted to. You can answer part B. We know a tangent line sketch looks about like that. It doesn't have to be perfect. You don't need to bring a ruler or anything like that to the final exam. Just sketch a tangent line like we've been doing in class, like you've seen in the reading. And as long as it goes to that point, it comes through like that, very close to the red curve when we're near -5. I'm not going to be too judgmental on grading that. Only way you might lose a point is if your tangent line looks something like, say, this. Doesn't connect through in that way whatsoever, so that's one way you could lose some credit. Or if your tangent line, say, just fully misses, it goes like that, you might lose credit in that way as well. So drawing the tangent line first is kind of weird because we're doing the problem out of order, but it also tells us the slope is negative, so that's kind of a check on our work. And here, you could use the definition of the derivative, the limit of the difference quotient, but I would only ask you to do that if the instruction specifically said, use the definition of the limit. And I believe for this final exam, I didn't go for a problem like that one. I'd want to keep it a little bit shorter. So you can use any method you want to get this tangent line. If any method is on the table, here's what I would do personally. We were doing this starting out in section 3.3. Start off by differentiating it. I'll use Leibniz notation, dy dx. This derivative, using the power rule multiple times, gives us 2/5 x plus 1 from the second term, 0 from the constant term upon differentiating. So step 1 is just get the derivative. Step 2, if we're building a line, we need a slope. So I'd state m equals dy dx. We're evaluating it at the point -5. And this is all just one big set of fancy notation. We'll come back to this and say a better use for it. But that notation is just saying plug -5 there. So 2/5 times -5 plus 1. The numbers kind of work out here. So this becomes -2 plus 1 for a -1. You notice that looks about right. This is a negative slope for sure. It's roughly like at a 45 degree from the negative x-axis. So that would make sense for a slope of -1. So that fits the picture. Next thing we have to do to finalize the problem is we need to actually find the actual tangent line. So we're building an equation on the next step. Any questions or comments first through these stages? Okay, well, pick your favorite way for writing the equation of a line. My go-to all semester has been y minus y1 equals slope m times x minus x1. The slope m is the one we paid the most attention to in the problem, but we need to be careful with x1 and y1 to get everything in just right. So substitute into that equation, y minus 1 is slope m. I'll write it as just a negative sign as opposed to -1. Up to you how you'd like to notate that. X minus x1 is x minus -5. So this becomes y minus 1 is -x plus 5. Getting there. So now y minus 1 is -x minus 5. Finally, add 1 to both sides, y equals -x minus 4. So that's the equation of the tangent line in slope-intercept form. I believe WebAssign forced us to write in that way. But you know, at this stage, it is simplified, and that is an equation of a line. If you're a little short on time and you just stopped right there, that's full credit. The instructions didn't say what format of a line specifically. That's the point slope form. an equally valid equation for the line. We have the line sketched down below. It looks like it fits this. The y-intercept is down at -4, which the arrow is seemingly going down about that value. Again, doesn't have to be perfectly drawn. You don't have to put points on here. Just give me a qualitative sketch of what that tangent line should look like. Double check it matches your information here. And that was the role of the derivative. We were, say, in sections 3.1, 3.2 when we were looking into this, calculated it differently, but now we've got a lot of great tools to do this computation faster. Well, we'll see what we're getting into next, probably more derivatives. Any last thoughts or comments before we turn to the next page? Okay, I think this one is a good one to emphasize because I don't think this was on WebAssign. I don't think we did this as a class or in a quiz. So this might feel like a random problem out of nowhere if you're asked to sketch a tangent line. So definitely review that, practice it, see what we did before, and this is basically what it boils down to. I guess we're skipping around a little bit. Example 3 is kind of like the end part of chapter 3. After we do that, this one is an application problem with derivatives, interpretation problem. Then we'll practice taking derivatives itself. But maybe this is good. Let's get this one out of the way while the class is not that far along, because this is a pretty decent application problem as well. I want to put here, as far as the final exam goes, I had to pick a problem for the review we're doing today. And when I wrote the final exam, I used a random number generator. And so on the real final, expect either exponential growth, like this problem, or decay. I used a random number generator to essentially flip a digital coin. To pick the problem, it will be exactly one of these two. This one's the growth, so if you folks would like to see an exponential decay problem, let me know. I can bring that to class next time. Well, let's get started on this one. Find an expression for the number of bacteria after T hours. Now, this formula is not on the formula sheet for the final exam, but I remember this was a comment made by a student in class. I don't think a student is here today, but there is a pretty cool formula that goes K equals 1 over T times the natural log of population size at time T divided by population size at time 0, initial population size. So someone cited this formula when we did this all the way back in chapter 3. I thought that was a pretty cool formula. I practiced with this today. So if you like to go that route, completely valid. I'll do it in the standard way that we did it in the notes that the book discusses. So I'm just mentioning that as a formula you would have to memorize to use, but if you like it, if that makes sense to you, feel free to use it. So to start off this problem, probably what I would do is begin by organizing. It says the bacteria count was 500 initially, so we have an initial value. We write that in as P of 0 is 500. We're also told bacteria count was 39,000 at 4 hours, so we have explosive growth, but usual. Population size 4, 39,000, makes me wonder what kind of bacteria strain this might be. We're also told the bacteria culture grows at a constant relative growth rate. That exponential is telling us exponential growth, and it's also telling us the growth model is P at T equals P at 0 times e to the power KT. We have the initial value. The value for K can be done in a couple different ways, but now all we're doing is building the function. So take that information and rewrite this as P at T equals 500 e to the power KT. Our job now is build K. You can plug in P at 4, 39,000, divide by P at 0, 500. Do the division, 4 would have to go there. So it's a kind of a tricky formula, honestly. Or the algebra is tricky in its own right. Just depends on which one you're more fluent with. I have a feeling a lot of people practiced in this particular way. So let's mirror this approach. Take P at 4 equals 39,000. What this formula did is it essentially took this model, solved for K, and did it in one shot. We're doing this in stages. We're taking 4, plugging it in right here. So this becomes 500 e to the power of 4K equals 39,000. So that 4 goes in spot of that variable t. Then 500 surely divides 39,000. So this is the standard reminder. Don't forget to bring a calculator. 39,000 divided by 500. There's not a ton of calculator work, but some problems are pretty much required. 500 will go in there exactly 78 times. So e to the power 4k is 78. Next, take natural logarithm of both sides. If you didn't write the natural log of the left-hand side or the base differential, good on you. That's a good shortcut to take. We're writing it in the notes here just as a reminder and an emphasis. They undo one each other. They're inverse functions. So the base e exponential is canceled by the natural log. Essentially, all we're doing is taking this equation here, writing it in its logarithmic form as 4k equals natural log 78. So here at the red dot, it's the exponential form. Same equation down here in logarithmic form. Divide by 4, and now k is natural log 78 over 4. So if I see that you've got to 500 on paper, you've got the k value, that is for full credit. But just to help out with part B, it's not a bad idea to write out, summarize, because we're going to put this in the calculator anyways. Population size at time t is 500. E to the power, it flows a little bit better if we put the variable t first, like we did in class. So I'll put that first, swapping the order. Then natural log 78 over 4. So there's the model. Now it's all about computations. So kind of a long problem. If it's a growth problem, these go a little bit longer. This is a faster approach, plugging in numbers. If it's a decay problem, then those tend to be a little bit faster because you can now use the half-life formula to speed up the solution for k on that equation. So I've adjusted the exam based on which version we go for, so the exam is not too long either way. Nomi says, would you take off points if we use a rounded value of natural log 78 for us? No, not at all. That'd be perfectly fine. What you should do is keep something along the lines of maybe 4 significant digits at minimum. But I wouldn't be too worried. If I can track your algebra and your calculus with your approximate value, I'm absolutely okay with that. WebAssign is sometimes picky if you round too bluntly, so that's the only place to be a little bit more worried about. Other questions so far? Okay, so now this is the computation side. We want to forecast number of cells in 2 hours. Interpolate P at 2 is, citing the model above, 500 e to the power 2 times natural log 78 over 4. This is one of those rare times where, because we're putting stuff in the calculator, it's not a bad idea to simplify this as it stands on paper, less stuff to type in. 500 e to the power natural log 78 divide by 2. So I just took this 2, divided into the 4, and depending on the calculator that you bring to class, that could be a good quality of life step right there, making it slightly easier to put everything in. For illustrative purposes, here's what it looks like. If you have a calculator pulled up right now, let me know if you are getting weird values. I'll definitely look into a different way to look into this to help out with the calculator. So on this one, I'm getting 500 e to the power natural log 78 halves, which is telling us to the nearest cell rounded 4,416 cells. So that's our first big computation for this sample exam. Any questions at all, folks, getting that number? Okay, next one, this came up on, I believe, a quiz probably. It definitely came up on an exam question where when it's asking for the growth, this becomes kind of the trickier end. So let's be really careful with this one. First, there's a formula. Let me check the notes because I'm not sure if I recall. Yeah, it's that right there. Let's throw this whole thing into our review just to emphasize that's where the formula comes from. The solutions to the differential equation dy dx are the exponential functions. We use p in place of y. Y is like a placeholder where it can be anything depending on the context. P for population, M for mass, or similar ones we've used. But this right here is the formula. If we write it in our notation, it says dp, x is time, so dt, equals k times population size for y. So that's the formula. All this is saying is the derivative of the population size is the growth rate, k, relative growth rate, multiplied by the population size. So we want to know this value at 2 hours. So if you wrote this next line, dp dt, evaluated at time t equals 2 hours, we're saying the same essential thing, except now we're just putting in k times p at 2 hours. So the 2 hours just goes here, which is nice. We have a value ready to go, the 4,416. For these kind of problems, I'm usually expecting you to use their rounded value here, but up to you. So let's take k, this part here, natural log 78/4, multiply it against population size 2 hours in 4,416. When we get a value out on that, here's what it looks like. If you're doing it exactly, just multiply by k here. If you're approximating like I'm about to, you'd probably go natural log 78/4, or an approximation of that in this spot here, then times the value you got, maybe slightly off depending on how you rounded, 4416. And this one's to one decimal place, 4809.8. This one didn't ask for units for full credit whatsoever, but it's not a good idea to put it in as a reminder. This is in terms of cells, because that's what the population was, number of cells per, the unit is a rate, so it's going to be per that denominator there, hours, or just hour. So 2 hours into this experiment, whatever we're doing here with these cells, that's how fast it's growing. Well, any questions at all, folks? Okay, pretty impressive growth when you look at this. If there was 4,416 cells at hour 2, the rate of growth exceeds the population size, but that's not terribly surprising for an exponential model. These things have doubling times that are really short. They grow extremely rapidly. And in this problem, 39,000 cells in 4 hours is explosive growth. Again, I'm not sure if that's appropriate in biology settings. I'm not sure if there are bacteria that really grow that fast. I'd probably have to do further research to see how plausible that number even is. But let's check out the next problems. The next one is another applied one as well. It flows a little bit different. The purpose of part 4 is we were in chapter 3, probably around sections maybe 3.3, 3.4. We did problems where we're looking into the growth rate of trees, or maybe something like this was also on exam 1. This one has an additional part, so that's why B and C are revised. I forgot to re-letter these. We're going to compare a function evaluation against a derivative value, and then explain what the derivative value is in context. These are tricky problems, and I think I remember seeing a request for someone saying we should try more of these, so here's our opportunity to try another one. Again, there's one on exam 1. You should expect something like this along these lines on the final exam as well. So I had a typo. This said rate. Sorry about that. So I noticed just this afternoon, I meant to say rat. This is a rat, a laboratory rat that's being grown. Its body mass in grams, T weeks, is modeled by the function here. So mass of this rat at T weeks into its life, it's only valid for the very first 10 weeks of its life. After a while, the growth model in grams for its mass is going to change. But for the first 10 weeks, it's probably growing pretty fast. And this is our model. So there's an initial value there, probably because, again, they don't start with zero mass. It's born, it already has some amount of mass. So that's what that part of the term is. Starts growing, but then this is going to be a tapering term. Its growth rate is leveling off towards the end part of the 10 weeks. First part is kind of nice, just a function evaluation, but watch for this part. I'm not going to assign a lot of credit to it, but for full credit, this is asking for the right units. So mass at time 4 is just plugging 4 in for t. 50 plus 45 times 4 minus 1.5 times 4 squared. This one is meant to be just tossed into a calculator once we write it down. So 50 plus 45 fourths minus 1.5 4 squared gives us 206. Because we calculated m, and in the context we were told that this was mass in grams, the correct unit for this problem is 206 grams. So 4-week-old rat is 206 grams. Any questions with that one so far? Okay, next. This one has a prime on it, so that says we're doing a derivative this time. It's a good idea to break this one into stages. First, calculate the derivative itself. The rate of change of the mass of the rat at time t is going to be 0 due to the constant multiple rule. Excuse me, due to the derivative of a constant rule, rather. Derivative of that is 45 minus 3 times t power 1, or just t. So step 1, get the derivative. Step 2, we want to know the rate of change at time 4. So we could call this m prime, continuing to call it that. M prime at time 4 is going to be 45 minus 3 times the value for t, which is 12. So 45 minus 12 will give us m prime at 4 equals 33. So that's our derivative. And it can be tricky. We've done several problems like these. The last problem also was a unit problem, although it wasn't required. But any volunteers to say what the unit should be for that? Sorry, say again. It'll be grams for the numerator and then something for a denominator. It'll be grams per something. Anyone see what should be in that denominator for the rate? Oh, sorry, missed that. Chat popped up. Yeah, absolutely. Good call, Naomi. This will be grams per week. Absolutely. I feel like this one's tricky because this one's in Newton's prime notation. So another way to kind of visualize this and to see what's going on with the units is you could write m prime at any time value t as really being dm, the derivative of m, dt with respect to t. And that helps because once you've written it this way, you can just look up the variables. The mass variable is in grams. That's why we have grams in the numerator portion of the rate. The time variable is in weeks. If it said hours, we'd change to hours, but this is in weeks. And so that's why we have weeks in the denominator. So this is one of the nice uses of Leibniz notation. It tells us exactly what's going on in any kind of unit analysis type problem, like this one down below. Again, it won't be for a lot of credit. The reason I'm going to ask for a unit on these problems here is mainly to help out with what's going on in part C. Once you notice that the unit is grams per week, it really directs us into the right interpretation for what m prime at 4 is. Because the interpretation here is not that the rat is 206 grams in 4 weeks. The derivative is always a rate of change. So what we're saying is, how fast is the mass changing at 4 weeks when we ask for an interpretation here? A fast way to say this is the rat is growing at the rate 33 grams. I'll write in the same way, bar for per week, when it is 4 weeks old. So we take whatever the derivative spat out at us, the prime is saying rate, dm dt is also saying rate or rate of change. We also have to take this information for the full interpretation because that rate of change depends on the week. If we're at, say, week 9, it's not growing that fast any longer. It's changed quite a bit. So these are the two elements for this kind of interpretation. Okay. Well, that's the conclusion of problem 4. What we're going to turn into next is just a list of different derivative problems for us to practice out. But any questions or comments so far? Okay, going off to the next example. There'll be a unit where you're finding derivatives like this one. I think this one might be about the right same length, but this problem I think I toned down a little bit. Think of this one down below, part D, it's kind of a challenge problem. This one's a little bit rough, but you know, we'll practice it anyways for the sake of practicing our exponential, or excuse me, our logarithmic properties on that one. The rest of them are pretty routine. You should expect ordinary power rule problems, a little bit of work with exponentials, a product rule and a quotient rule. So we'll solve each of these in turn, step by step. First, taking the derivative of this one is a little bit nasty in the sense if you start out just right away. You definitely don't want to use quotient rule on one term. That's a lot of work. The derivative of this is not the derivative of the numerator, divided by derivative of the denominator, and neither is the antiderivative. What we really need to do with this one to start off is just fix that exponent. Rewrite as f of x is -3, promote the base x up into the numerator, and now the power is a negative. Then plus 9 natural log x minus 5 power of x plus the natural log of 6. So when we go to calculate this thing, we can say f prime at x in a much easier form. Really only one term was problematic. Here we take -4 times -3 for a positive 12. Power of x goes down. We need to be careful now that we have antiderivatives. So go down when you differentiate. Those words kind of help out. You know, that's not a bad thought to convey here. Differentiation means go down in power. And antiderivative, anti just means do the opposite. Power is going up. So if it was -4, now it's a -5. Plus, the derivative of a natural logarithm like that is really nice. All you get is 9, x goes into the denominator. This one's tricky. This one goes -5 power of x multiplied by the natural log of 5. And this one is tricky as well. This one might be the trickiest one in the whole set of terms. This one is a constant. We'll only have natural log x turning into a 1 over x, so 9 divided by x altogether. If there's an actual x there, that makes it a bona fide function that varies. But this, if there's no x and you differentiate it, it's gone. It becomes 0 in the derivative. So that's one derivative down, just going term by term. Any questions before we check the power rule, or excuse me, product rule problem? Okay, our next one, the big rule to review here, is going to be product rule. So the product rule goes like this. If you take f times g prime, you get f prime times g plus f times g prime. So that's the way we stated it in the notes altogether. There's other ways to state this. Some people make that term come first, but you can change the order of addition. Major takeaway, though, is you just have to make sure you differentiate one and then the other. And the reason I write it in that format, we mentioned way back in the day when we were introducing these, is mainly to help out with accuracy with quotient rule. And quotient rule, the order matters because of the negative sign. And a great way to memorize the quotient rule is to get the product rule down pat. Then you copy it, but swap to a negative here. F prime g minus f g prime. Then you don't differentiate in the denominator, you raise the denominator function g to power 2. So those are our two sets of schematics for dealing with any product rule, any quotient rule. And you can possibly do these quite fast if you've had a lot of practice. But because it's a review, our goal is not to rip through it. Let's do these carefully for a good overall review on both of them. Here's a great way to next analyze. Whenever you have a complicated formula you're tracking, it's a good idea to think in terms of colors. It helps the mind determine what part is what component goes to what component when we look into the formulas. So if you think along those terms, g prime of x becomes this structure. You can factor out 18, but when we did this in class, we usually just kept the 18 glued on in this way. So I'm going to do it in the same order. 18 times x cubed prime e to the x plus 18 x cubed times e to the x prime. So I mainly use color coding to show where the derivatives are going to occur, but copy in the same order. The function f and g are repeated, and all we're doing is moving where the prime symbol is. Once we got that down, we're basically done. We just need to do two derivatives, one of them of which is the nicest all-time derivative. So g prime of x is 18 times 3. I think that's a 54. Let me know if I'm off on that. 54x squared. So that's one derivative down. Let me color code it to say that's a derivative we took. Everything in black we're just copying in, plus e to the x plus 18x cubed. And again, here's the nice derivative. The derivative of that one and only exponential is exactly itself. Never changes. So at that stage, we're done. It's up to you if you want to do anything further. You can factor out 18 e to the x. Or you could do even better. You can factor out 18x squared e to the x. But there's nothing further we're doing on this. We're not optimizing it. We're not finding concavity. If it's just differentiate and you're doing a final exam, it's probably a good idea to end right at that stage rather than getting too carried away. If you did simplify it further, you made mistakes, I would grade on this line right here. Right where the calculus ended, I'd still give full credit. Well, next up is quotient rule. Any thoughts or comments with the ones we've done so far? Okay, so quotient rule, same idea. Let's go really carefully with these. It feels bigger because there's more moving parts. But the thing I forget the most is sometimes I just do product rule too much and I forget a negative sign there. And it's embarrassing, but sometimes you can forget the power too. So watch out for those two elements in quotient rule. So let's write this out carefully again. Y prime is going to be a fraction that goes like this. Let's do this in a slightly different style. If you like the placeholder method of saying function composition or these kind of rules, as a placeholder method, this is what the entire quotient rule is. So you just now plug in your values. We did this kind of strategy a lot. For example, whenever we did a chain rule problem. So 5v minus 3 will go here and here. Once you get the f function solidified, all remaining positions are for the denominator function, the one usually labeled as g in the quotient rule. So e to the 5v and below. Below here is my meaning, and also on the two spots in the numerator. Now, this is an exponent law down below. This is going to become e to the power 10v. If you left it in that format, I wouldn't say it's super harmful. But the next thing I need to recall is there's a mistake on paper. Recall that there are two primes. Sorry for that mistake, but let me kind of highlight it. Product rule has those primes. Quotient rule also has those primes. There's two additional derivatives you take when you set these up. So don't forget that prime symbol there. Let me make it just a little bit bold and highlight it. Why not? I mean, it seems silly, but if you forget to put the prime symbol and you're writing down problems on a final exam, it could trick your brain into forgetting to differentiate it too. So that's a critical thing just for accuracy. Be sure to write that in. But now we're basically done. So derivative of 5v minus 3 is just a 5. This is a copy step, so e to the 5v. Another copy step, 5v minus 3. And, well, this breaks a pattern that we'd like to see. Derivative of e to the x is e to the x, but this is not the same kind of exponential. That's a function composition. So out of nowhere, a chain rule comes up. Sometimes it's not a bad idea to divide and conquer, so let's pause that derivative. Let's put an arrow as a reminder and erase it when we come back, because now we want to differentiate y equals e to the power 5v through chain rule. Easy to miss. I'm great on partial credit. So if you miss the chain rule on that, let's say this is a 5-point problem, you're possibly going to get 4 or 5 points on this kind of problem once I determine the rubric. So it's good to be accurate. Let's make sure we hit all the chain rules. Let's do our typical chain rule analysis as well. In these analyses, we indicated what was the inner function, what was the outer function, and it was not always easy to tell. It depends on the function. Exponentials were among the trickiest. I got the most classroom questions for these kind of derivatives. The thing that got plugged in, an ordinary e to the x that changed it into a chain rule, is the inner function. So that's what is on the inside of the exponential, changed to a 5v, so that's derivative 2, inner. So that's the innermost function. You can emphasize that if you'd like by putting a parenthesis around it. Depends on how you want to notate it. That means the outer function is this, the base E exponential. Y equals e to the v is outer. We just happen to put something in place of v that's not strictly v itself. So if that's the function, and that's our analysis, y prime, through the chain rule process, looks like this. We're going to do what we did like with the quotient rule, write down the schematic, the placeholders. It's going to be, go in the order of these derivatives. The derivative of e to the v is itself, so it goes like this. But it's not just v, so we put in a placeholder, and then every time we've done a chain rule, we've chained on the next derivative. So that's the entire structure. Now, once we have that down, we're done with derivative one. Outer function derivative is done. This is the chain rule part of the outer function derivative. Move to the inner function, and whatever is in there, no matter how nasty it looks, just plug it into the placeholders. They'll go both here and here. But now that we see the process, we can see doesn't matter what multiple of v that was. If it was 13v, the derivative is just going to be 13 times e to the power of 13v. If it's 5v, the derivative of 5v is just 5. So this resolves as y prime equals e to the power of 5v times 5. So that whole thing here gets dropped following that arrow when we take that derivative. I'm going to usually write it as 5 coming first, so I'll go 5 e to the power 5v. Where the multiplication bullet could also be ignored if you like as well, make it slightly better shorthand. So 2 derivatives down. This one was like a side quest with the chain rule, but that's good. That's good for the sake of review. Denominator, we're going to square that out and get e to the power 10. The outer exponential multiplies 5v, so it becomes 10v. Sorry, I forgot the v there. Glad I took another look at it. 10v altogether. So this one was definitely tricky. I'm great on partial credit, so if you've got the chain rules, the quotient rule structure down, that was the main thrust of the question. If you have the derivatives right, then you're pretty much done. And again, I'd probably leave it in this form. You might get some like terms to simplify just a little bit by factoring out 5e to the 5e, but the calculus is the main emphasis on this one. Unless you're optimizing, doing anything further, that's probably a good stopping point. Naomi says, will we not have what a derivative of a log is on the final, like the equation? Well, let me double take a look at that. So for the final formula sheet, I have, let's see. Yeah, it looks like that one's going to be considered a formula that we do have to memorize. But you know, there is a hint here. Because this is an antiderivative problem right here, it actually does double duty for us, and so does this one here. So if you take this formula that is provided on the real exam, you can rewrite this by saying, well, how do you check an antiderivative formula? You differentiate one side, and it has to equal the thing in the middle right here. So this formula also tells us that d by dx of natural log x or absolute value, either version, I'll go with this version, since that's the one that's we're typically thinking about, is 1 over x. Likewise, this one will tell us as a formula that d by dx of a to the power of x must be a to the power of x times the natural log of a. That's how that natural log of a down there is going to get wiped out. So yeah, those are 2 formulas that we would have to have memorized for the real final exam. I think this one is more typical that comes up, but we should be ready to go for this one as well. I think that's a good comment to put in the notes as well. Let me put it in right here. Along similar lines, another formula that we need to have memorized for the final exam is if it's a different logarithm, say d by dx of log base, let's just call it base b, generic base of x. It follows this process close, but it's off by a factor in the denominator. X times natural log b is what we would get altogether. Other questions so far? Okay, well, this one again is kind of a challenge problem. It's nastier than what will be on a real final exam. There's lots to study here, but the idea with this one is we need this information here to assist us. So we had a question along these lines that was on exam 3. It was broken into two parts. Part 1 said, simplify first using properties of logarithms. And the second part said, differentiate your answer. We also had something like that in the lecture notes as well. And so on the real final exam, just to throw another hint out, expect another problem just like that. Again, not for as nasty of a function. I simplified it quite a bit so we can get right to the major punchline and not spend all day differentiating. This one is a review problem, so it has a little bit more going on. So organizing it kind of has the final exam questions going to look. Part 1 will be simplify using properties of logs. Then part 2 will be differentiate the answer in part 1. Okay, well, we've got 4 minutes to do this. We might do the part 1, but leave off the derivative portion of the second part when we come back on Thursday's review. But let's give this a try. Let's break this down to stages. H of t, we don't call it h prime yet because no calculus is occurring. This is just now pure algebra. First rule we want to use is the quotient rule here. This is going to give us a difference of logarithms where the x is this piece and the y is that piece. So if we follow that rule to the letter, we'll say that h of t is the natural log of x e to the power 10x minus the natural log of, let's also fix the exponent on that. It's a square root, so it means it's really parentheses 2x minus 11, close the parentheses and put in a power of 1/2 really. That'll allow us to use property 7 coming up down the line. So that's one property down. Next property, I'm running out of colors for color coding, but we're going to use the product rule right here. The product rule gets used on just the very first term. So what it says is there are two things being multiplied together. There certainly is if we emphasize with a multiplication bullet point there. You can make that a log, natural log x plus natural log e to the power of 10x. So new line, natural log x plus natural log e power 10x is what we can put in, minus natural log of 2x minus 11 power 1/2. So that's how that step goes. Now we have 3 different terms, and every property you use simplifies even further. One that was missed, the most common one missed, say on exam 3, was the exponent property right here. This is a difficult chain rule without moving that, but any power, even 1/2, becomes a coefficient by property 7. And we have used this property a lot. We used it in the notes already today. The cancellation property, number 1, it has a reversal for property 2 if that comes up, but it goes like this. We did that in the exponential growth problem. Natural log of base e is a cancellation as well. So this means what we're taking is h of t is natural log x plus 10x minus 1/2 natural log 2x minus 11. 2 of these derivatives are nice. The third derivative is not too bad, but it becomes a chain rule, so we'll have to carefully analyze this one. When we go to the next part, differentiate the answer that we produced. And even if we didn't do everything, maybe we stopped on this line right here, still give your answer derivative a best shot. Still great on partial credit with these, whichever line you ended on. But the further you go, the more properties of exponents you use and abuse to get through this, faster that part is. Well, this is probably a good stopping point for us. Sorry for going to less than 15 seconds to go. But any last questions or thoughts, folks, before we call it a day today? Okay, well, next class, we'll move forward in the notes. I'll take any questions you might have first. We're going to be getting into minimum, maximum values, some optimization. So we'll take our time with these problems. Then we'll be looking into antiderivatives and fundamental theorem of calculus, evaluating the integrals. So that'll round out our review. But have a great night, folks. I hope the reviews are going well for your other classes. We'll be through it before you know it. Take care. Have a good one.